Welcome to AP Chemistry at Hononegah High School. I'm Brian Brown, and today we'll be looking at our next section of notes over Chapter 19, which is Part 4, which predominantly deals with Section 19.5, dealing with Gibbs Free Energy. But before we get to that, I've got a little bit of 19.4 I want to clean up. And I held off on talking about this in our previous set of notes because it leads directly into what we're going to be talking about with Gibbs Free Energy. Now, heat that flows into or out of the system changes the entropy of the surroundings. So what's happening in the system is having an effect in the surroundings. For an isothermal process, a constant temperature process, the delta S of the surroundings would equal the negative delta S of the systems over the absolute temperature. Now, we looked at this before from the system's point of view, but systems energy is going to be the opposite of the heat in the surroundings energy is going to be the opposite of the heat of the system. And also to add to this, if you recall from Chapter 5, if this is a constant pressure situation, then Q, the heat, would equal the delta H of the system. And therefore, that's going to end up being a substitution we're going to talk about in a second with Gibbs Free Energy. Now, the universe itself is composed of the system and the surroundings. So when we look at this from the viewpoint of the universe, remember it would be the entropy change of the system plus the entropy change of the surroundings would be the overall entropy change of the universe. For a spontaneous process, the delta S of the universe is always going to be greater than 0. Because even though the system may have a delta S of 0, the surroundings are still going to be changing in entropy, and that's going to give us an overall increase in entropy for the universe. So for a spontaneous process, the delta S of the universe is always going to be greater than 0. And that's going to be important when we get into the concept of Gibbs Free Energy. So there's a couple of things we've looked at in these last two slides that are going to apply when we get into section 19.5, Gibbs Free Energy. So recall the delta S of the universe would be the change in entropy of the system plus the change in entropy of the surroundings. And the change in entropy of the surroundings would equal negative Q of the system over T. And if we're at a constant pressure situation, Q would equal delta H. So therefore, that equation up top through substitution becomes the change in entropy of the universe would be the change in entropy of the system plus the negative delta H of the system over the absolute temperature. Now, if we take and multiply that equation on both sides to maintain the equality by negative T, we get negative T delta S of the universe would equal the enthalpy change of the system minus T delta S of the system. Now that negative T delta S is defined as the Gibbs free energy, and we call it delta G. So delta G is really negative T delta S. Now, if we substitute that into the equation, what we really get is our Gibbs free energy equation. Delta G equals delta H of the system minus T delta S of the system. In a second, we'll look at a little bit more about what Gibbs free energy really is. At this point, I want to look at a little bit closer what's happening in this reaction system here for delta G. So what is this equation really dealing with? Now, first of all, remember delta G is really negative T delta S of the universe, and that's going to equal the enthalpy change of the system minus the T delta S of the system. Now, when delta S of the universe is positive, delta G is going to be negative. So because it's negative T delta S equals delta G, when the change in entropy of the universe is increasing, the delta G is going to be a negative value. It's going to be one of the things we use delta G for, is because when you have a negative delta G, that means something specific we'll look at in a second. Now, for a spontaneous reaction, the delta S of the universe is always increasing, which means it's going to be a positive value. Put those two ideas together. So therefore, when delta G is negative, a process is spontaneous. And that's a really important idea. When delta G is negative, we have a spontaneous reaction. So whenever delta G is negative, we know our reaction is spontaneous. Now, under constant temperature and pressure, the sign of delta G is therefore a predictor of spontaneity. If the delta G is negative, then the forward reaction is going to be spontaneous. That would be an example of a product's favored equilibrium situation. Now, if the delta G is 0, then that means our system is at equilibrium. So whenever delta G is equal to 0, we know we have an equilibrium system at equilibrium. And then finally, 3, if delta G is positive, that means the forward reaction is non-spontaneous. And that basically means work must be supplied from the surroundings to make the reaction happen. And the magnitude of the delta G is going to tell us how much work we have to do on that system. Just like in number 1, when delta G is negative, that's why we call it Gibbs free energy. That's going to tell us how much energy is freed up in the spontaneous reaction that can be used to do work on the surroundings. Now, the reaction is spontaneous if it's a reversible reaction then when your delta G is positive. So if our forward reaction, the delta G is positive, that means the reverse reaction would be spontaneous if it was an equilibrium system. But the real big idea here is when delta G is negative, that means the forward reaction is spontaneous. If delta G is positive, that means the forward reaction is non-spontaneous. And the magnitude of your Gibbs free energy would be how much work has to be supplied to make the reaction happen. So delta G and delta S of the universe are both predictors of spontaneity. We've tied that idea of spontaneity to both of these values now. But only delta G relies on the system, and it's a lot less complicated to figure out whether a system is spontaneous or not by looking at delta G. So while it is true what we talked about earlier with the delta S of the universe and its sign telling us and predicting spontaneity, really it's delta G that's much easier to calculate and look at for different chemical reactions, because delta G is specifically determined by what's happening with the system. And those are values that are much easier to calculate. So for a spontaneous reaction, remember, delta G would be negative. And the magnitude of the free energy change represents the maximum amount of work that the system can do to the surroundings. So the value of delta G would equal the negative of the work maximum. So how much work can that system do on the surroundings is basically what a negative delta G would tell you. In the case of a non-spontaneous situation, positive delta G, the magnitude of the free energy change represents the minimum amount of work that must be done on the system to make the reaction occur. So not only is the sign important, but the magnitude of the value is also important. How much free energy is being freed up by the spontaneous reaction to do work on the surroundings versus how much work does the system or does the surroundings have to do on the system to make that reaction work. Now, equilibrium position and Gibbs free energy. So we're going to look at what's happening through the course of an equilibrium situation and relate it to the concepts of Gibbs free energy. So if delta G is negative, that means the forward reactions move spontaneously towards equilibrium, because that means the forward reaction is going to be spontaneous. And that's really what's going to happen if we calculate the Q of this reaction and find out it's less than K. If our delta G is negative, we know we're going to be spontaneously moving equilibrium to the right, or moving to the right to achieve equilibrium. If the delta G is 0, then we know we're at the situation where at the bottom of this free energy well here, and that would be when Q equals K. So a system at equilibrium, our Q value would equal our K value at that particular time, and delta G would equal 0. And if we are to the right of equilibrium, that would mean the forward reaction is non-spontaneous, the reverse would be spontaneous, and we're going to spontaneously move equilibrium to the left to achieve equilibrium. And that'll happen whenever Q is greater than K. So to tie this to equilibrium that we're talking about in the last few chapters and the concept of Q, we can actually look at our current delta G for an equilibrium reaction to see whether Q is going to be less than, equal to, or greater than K, and which way we're going to be moving to achieve equilibrium. Now, analogous to standard enthalpies of formation, the standard free energies of formation are delta G sub F. And that little circle once again means standard state. We're going to talk about more about that formally in a second. But what this really comes down to is like delta S and delta H and E, delta G is a state function. So the sum of the formation Gibbs free energies, the products, minus the sum of the formation Gibbs free energy, the reactants, would equal the delta G of the reaction. And notice all of these things have those little zeros there, so it's delta G naught. That basically is how it's pronounced, but that would mean we're at standard state conditions, which we'll look at in a brief second. Now, just like the values in the tables before were always per mole amounts, they are now as well for delta Gs. So remember, you need to multiply the amounts in the table by how many moles are in the balanced chemical equation. Now, I've briefly mentioned this before, but I want to formally look at it now. Like standard formation enthalpies in Chapter 5, and entropies that we looked at in yesterday's notes. The standard in the term standard values imply a particular set of conditions. Now, the following conventions are used when calculating standard free energies. So whenever you see that little circle, that delta G naught, delta H naught, and S naught, what it means is we're under standard state conditions, which if we have solids, they must be pure. If we have liquids, they must be pure. If we have gases, they're at 1 atm pressure. If we have an aqueous solution, it must be 1 molar concentration. And for elements, the standard free energy formation of the element is its standard state as defined as 0. So what we're really talking about here is these very specific conditions whenever we're talking about a situation where we have that little circle there. So standard values, which is what that little knot implies, imply these particular set of conditions. Now, since delta H naught and delta S naught do not change much with temperature change, we can assume use the same equation to measure delta G at temperatures other than 25 degrees Celsius. So if that little knot is dealing with 25 degrees Celsius situations, then for all intents and purposes, it's not changing all that much when we change temperature, so we basically assume it's the exact same value when we're at temperatures other than 25 degrees Celsius. So we can actually plug in the calculations for delta H and delta S and T to calculate what our delta G would be. And remember, technically this deals with values at 25 degrees Celsius, which would be room temperature conditions, but we can assume that the changes are going to be very, very minimal, so that basically we will not change much with temperature, and therefore it's going to be the same calculation. So as temperature increases, the importance of T delta S increases, because that means it's going to be a larger value. And remember, what we're really typically looking at here is delta G going to be positive or negative. Well, in relationship to delta H, when the second term here becomes larger, then it begins to dominate our discussion basically with what we're looking at. So as temperature increases, really the importance of T delta S increases. So at very high temperatures, delta G approaches the value of negative T delta S, because what we get for delta H becomes minimal compared to the two. Now, as temperature decreases, the importance of the delta H increases as negative T delta S starts to approach 0. So really, under high temperatures and under low temperatures, two different terms here are going to dominate in determining what our Gibbs free energy is going to be. If it's a high temperature situation, the T delta S dominates. If it's a low temperature situation, then the delta H starts to dominate. And one thing we can do to look at overall spontaneity of reaction is, by the sign convention of that last equation, you can see what has to happen to get positive or negative values, spontaneous or non-spontaneous conditions at different temperatures under a host of different delta H's and delta S's. So what we're really doing here is describing the relationship between delta G and the maximum amount of work that we can derive for spontaneous reactions, or the minimum amount of work that be required to accomplish a non-spontaneous reaction. That's really what the delta G is going to stand for. And if you evaluate this equation for the signs of delta S and delta H, you can see under what conditions you're always spontaneous, always non-spontaneous, or a temperature-dependent situation. And this is really what you should have looked at last year in honors chemistry. Looked at this from a very simplistic point of view. If delta H is negative and delta S is positive, that means you're going to have a negative minus a negative. Delta G is always going to be negative. So it's spontaneous at all temperatures. So that's why we said when it's exothermic and an increase in entropy, it's always going to be spontaneous. If it's endothermic, positive delta H, and a decrease in entropy, negative delta S, you're always going to get a positive value for negative T delta S. So therefore, it's always going to be non-spontaneous under all temperature conditions. The last two situations here are really where it's temperature dependent. If it's exothermic and decreasing in entropy, it can still end up as a negative value. It really just depends on what the temperature is. I should say, if it's negative and negative, it's going to be spontaneous, to be more specific, at low T's, and non-spontaneous at high T's. So when your delta H and delta S are both negative, it really depends upon that value of T as to whether you're going to be spontaneous or not. And then on the flip side, when you are endothermic and increasing in entropy, it's going to be spontaneous at very high temperatures, but non-spontaneous at very low temperatures. And that finishes the set of notes I wanted to deal with for section 19.5.